we're back at it. Basically, the part that was left was to try to figure out where is this whole thing coming from. And first of all, I uh, just wanted to show you the circuit that we built last time. And basically, if I understood well the Wikipedia, those are those are the different Y's, right? So the different results that we're kind of getting, supposedly getting, right? So here we're if I were to measure, because this is not really so this measurement, but if like this is, you see the chance of all the possible outcomes. So I'm going to take the four of them, and it's 0 0 0 0 0 1 and then 1 1 0 1 1 1. Okay. And so basically what I'm going to use is I'm going to use also a page that's called itty-bitty, which is pretty cool because it allows me to basically have here a, so I said 0 0 0 0 1 1 1 0 1 1 1, and this kind of gets basically, let's see if I can zoom in a little bit, and this basically gets it's all URL encoded, so I can just come back to it whenever I want. And so I'm going to save this on the side for a second. I haven't figured out yet how to switch, because I'm recording a browser tab, and I haven't figured out yet how to switch from one tab to another, so the recording, so I don't have to, because the bothers me a little bit that I have to keep tabs open that you don't see, and that I can then kind of switch from one thing to another. So once again, the idea, the high-level idea behind Sam's algorithm is to probe a quantum circuit enough times to find n-1 bit strings such that the following equations are satisfied, where the dot is the modulo 2 dot product, right? So this means each component multiplied, and then I guess that's the addition modulo 2. And so if you remember well from the, so we use this example, so S is 110. S is 110. So let's just double check. So we know that S is 110. So now what we want to do is this times 10, and this times 10, 10, and this times 10, and this times 10, and this equals 0. So this is what we're supposed to kind of prove as a system of equations, and in theory we just need 3 of them, because x, y, z, x, y, z, x, y, z, x, y, z, and so because you have, so remember this is a secret, so we in theory don't know it, right? So we wanna check what are these things, z, and that is hopefully going to be 1 and 0, because that's kind of the secret string, and basically what this translates to is right, 0 times x plus 0 times y plus 0 times z in this case, and that's kind of the useless one, I guess. There's always going to be one of those based on what I've seen in Simon's, in the Wikipedia page. That's what they say. But now, yeah, so you see, and so if we do kind of the same thing in here, you kind of realize that, well, based on this, basically z must be 0, so we can confirm that. If we do the same in here, now we basically have got the fact that we've got two those in here, but we know z is 0, right? So we know this is 0. So we know basically that x and y must be, so this is basically what these two equations tell us here. Basically, how does it look like if I use this here? It's so big. Yeah, okay, that's probably not the best idea when I'm zoomed in. Anyway, so what those two things tell us is basically that x plus y must equal 0. And this is the modulo 2, so basically the only way, and as x and y must be binary, so it's either, this must be either 0 or 1, so that's basically, there's no other possible solution to this, that x and y are 1, right? So we've confirmed those things as well. Good. So we got it working, smiley face, but I'm still intrigued by just the simple fact that so let me save that here and basically take you back to the Wikipedia page. So how are we coming to that? Basically? How do we know that that the system of equations must hold true? That's what's intriguing me, right? Because basically, if I take a look at the circuit again, right? And so you end up trying to reason how is it that you end up with that subsystem, so with that register being 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1. So this is just what happens before the Hadamard. So before the Hadamard, nothing happened. I mean, nothing happened. Is that you've got the same, right? So this must mean that there has been some phase, some basically some phase shifting in here, right? And that trace and that phase shifting is for some reason leaving you with a multiple of s, or something that's related to s, because then basically all the stuff that you're doing in here, pay attention. What it's saying is that all the state that you've got in here, every single possible outcome, when multiplied with s, it gives you 0. It's basically it's an XOR what you're doing with the multiplication modulo 2, is it? it's not. It's not an XOR. It's just it's that multiplication. Okay. How is that relation? How does that relation even come? Take a look at an amplitude display. I don't see the phases in here. That's the thing. Gotta take a look at the full system. But basically, all the phases are okay. If I move it here, all the phases are okay. So all the phases are untouched. All the phases are untouched. No. So all the phases are all the time untouched. I mean, that's what makes sense, because there's no here phase kickback or anything. So the only explanation is that that measurement really affects. And not really. Yeah, I mean, it has to be like that, because that measurement is what's affecting here. Because if I take a look at, if I move this around here, it's always the same, right? So there's no change in that subsystem. You always have a perfect superposition, and then all of a sudden that messes up. If we don't measure this, you still got the same issue. Well, yeah, because now you basically, okay, yeah, so stupid. It's not the measurement, it's the fact that now you've basically created entanglement that is actually, I mean, you've done some entanglement in here. See, because you come from, you basically here come from a, so if I were to add a Hadamard in here, you'd have the same issue, right? You'd have the same effect, right? Because amplitude changes, because what you've done is you've effectively created a bigger superposition that it's not that's not like a complete full superposition, because now you've got like a 6 qubits as your whole system, right? So you've entangled them effectively. You've created an entangled state. And so when you apply Hadamard to only part of that state, then so this is really where the effect is happening, because then you've got those things in here. Yeah. But then still I can't figure out how do those things, why does the let's go back to the to the Wikipedia. So why do those things, so where's that coming from? This is what I'm not so sure that I understand, but this maybe is explained later here. I explain mathematically, which is no, but it's not. Second case. Classical post-processing. When we run the circuit, there are two cases. In a special case where equals 0, the measurement results in each string y with probability. In the case where x is s, where s is not the 0 string, the probability to obtain each string y is given. Thus, in both cases, the measurement results in some string y that satisfies. This is what I've done. So I get that the fact that it's even means that this equals to 0 because it's a product. It's the dot product of the binary strings. So that's basically, if this is even, it means it will be a 0, right? Because it's when you do modulo 2, that's okay. So this I get, but then okay. So what this is telling us is if you run the maths, you're only gonna get strings that are strings that are even. So it's like that when you multiply them with s are even. So we've got, okay, so here they write the probability. Just don't like to go down to the level of the math to explain that intuitively. I'm just kind of missing that intuition. So this basically saying is that the numbers we get are always even when multiplied with s. Why is that? Why is that? Because another way this is explained, right, is that the measurement, that there's a measurement that happens kind of here, right? Whereas like we first measure that. What am I doing? Then we apply the Hadamard's, right? So if I take a look at the amplitudes, basically, no, the chances here, I see that really that's the wrong thing to do. So those are the possible things you can measure, right? Basically, are all the possible results. what I'm saying is, if you think of it in this way, it may be easier to explain, because then you say, let's pick an example, right? So let's pick these examples: 0, 0, 1, 0, 1, 0. 0, 1, 0. Let's see if there's another 0, 1, 0. So there's another 0 on 0. So you basically have a superposition of 1, 1, 1 and 0, 0, 1. And then when you do the Hadamard on these, you're basically going to get something that's, with 0. That's what it's saying. 0, 0, 0. 1, 0, 1. So 1, 0, 1. So 1, 1, 0. 0, 0, 0. So basically, sorry, I'm stupid. I mean, it's obvious that what we've got is that if you measure the f of x first, you're basically going to get that's interesting. See, what you're getting is 101, 101. There's always two values. See, given a function, must decide the property that from some s. Okay. I think I'll start the video here, because I think I gotta, because I'm running out of time right now. But this basically means, if you think about it this way, of course, if you measure the whole thing, you're basically gonna get subsets of the results. So you're gonna get, basically, for example, if you measure 101, you're gonna basically get that, right? So you're basically gonna get the 0, 0, 0 plus 1, 1, 0 superposition, right? And so what this is saying is that if you do now a Hadamard of this, that you're gonna end up with something that is a with something that is basically even when multiplied with s. Interesting. So the relationship basically is that between these numbers and these numbers, there's literally that, right? So this is actually the core of the whole thing. So you're, of course. So basically, what the algorithm is doing is then packing is basically, in this case, you're basically getting, every time you measure, you're getting subsets of effectively that superposition, and or I mean, of, maybe these, maybe if you measure 101, then you're going to get like these and these, right? So the 0, 0, 1 plus 1, 1, 0, right? 1, 1, 1, sorry. Yeah, which is basically has that s applied, right? And somehow the Hadamard then covers that. Okay, so this is what this is next. Okay, I'm gonna try to study how that interference works. So the next video is the interference in Simon's algorithm, and this is really hopefully the last one on this series. Basically, that's really interesting. So it's playing with entanglement and getting exactly to find the relationship between the entries, right? So that's what we're trying to find, is the relationship between those things, and then so you're kind of getting those kind of superpositions, and then when you when you apply Hadamard, that creates a destructive interference that really tells you what that is. Maybe it's just a stupid thing, but I feel there's something to understand in here, and that's basically what's attracting me to that, to spend so much time on just that algorithm. Perfect.